Okay, let's remember the way we do the modeling. Now let's me draw a very simple frame. Let's say that this is our physical structure composed of two columns and a beam. Okay, this is our, again, the physical structure, the actual structure. And one of the approaches, the modeling approaches that we discuss during the class is, let's say that this is the height of that member, and from center line to center line, that's the length of the beam. Okay. Now we said that usually in modeling we define these nodes at the story levels, and we draw members at the middle, at the center lines. Okay, and from that we generate our structural model, which is nothing but a wireframe model, right? So let's say that I model the foundations and spin supports. That's the beam. And this is my structural model, okay? The height of the columns, they are equal to h. And the length of the beam is L, okay? Now, this is usually the way we generate the model, but what we are actually modeling is this. I have a beam whose length is equal to L, and I'm modeling the beam from its center line, so I have a beam like that. And I have a column, and the column is modeled as follows. Okay, now we said that the actual length of the beam is actually this one. It's not L, but it's actually LB. Now this part where it intersects with the column doesn't bend the way the middle part bends, right? This part is much more stiffer when you compare it with the middle part. Now the question is, how can I consider this effect in my structural modeling? So one approach is to generate a model like that. So I have a column, then I have a rigid member. So I'm just modeling the column in two parts. This is our original node, and then I define another rigid member who cannot bend, and then I have another node here, the beam, and another rigid member node, another rigid member here, a node, and a flexible column. Okay, now if you say that that's the depth of the beam, so this distance, according to, if I just want to mimic this modeling, this distance would be equal to d over 2. So I have a rigid column, portion of that column is rigid, and this part, the below part, can bend more flexible than this part, so I just represent its behavior by a rigid member. Likewise, this distance is the flexible part of the beam, is LB in our case, and that portion, I'm here in this type of modeling, I'm modeling the behavior of this portion as rigid, and if I say that that's the width of the column, let's call it B, then this length will be equal to B over 2. Okay, that's one way of doing it. But if you just take a look at our original structure, basically I got 4 nodes and 3 members. Okay, and in this modeling approach, I have 1, 2, 3, 4, 5, 6, 7 members, and 1, 2, 3, 4, 5, 6, 7, 8 nodes. So I want to model the behavior of this physical structure in a more detailed manner by defining these rigid members, but in return I end up with more members and more nodes, in other words, more things to calculate, more degrees of freedoms. So of course today you can argue that okay, we have very fast computers, we can compute all of this, but modeling time to do all this for every beam column connection is requires very significant amount of time. So alternatively, this is what we do. So I'll call it alternative action or alternative way. One approach is defining rigid members. So the alternative way is formulate a new element. Okay, so I have a new element here. Some portion of it is rigid. And the ends of that member are rigid, and the middle is flexible. And the behavior of this member is described again by our classical 6 degrees of freedom in 2 dimensions for a plane beam. And you can actually use the same approach to formulate a 3D space frame element. Okay, so for this type of element, if I can find a way to generate a 6x6 stiffness matrix, then it will actually simplify my solution, and again I can use this many nodes and this many members. So the question is, how can we formulate such an element? Okay, so let's discuss that. So I'm now formulating a 2D plane beam element with rigid and offsets. So while doing that formulation, I will be using the transformation method, and I will directly obtain the transformation matrix. Okay, so the formulation is as follows. So I have some portion of that new element as rigid. So if it's at the start node, I will call the length as bi. So at the middle I have a flexible portion, and at the end again I have a rigid portion. This is bj, and in the middle I have lf, which I call the flexible portion. And these are the rigid zones or rigid offsets. And I want to represent, that's the start node, that's the end node, J, the behavior of such an element by using 3 degrees of freedoms, D1, D2, D3, D4, D5, and D6. Okay, so let's try to formulate this. Now I'll start with the relationship between the displacements. So I'm just dividing this member into 3 pieces. At the middle I have a flexible member, okay, whose length is LF, okay, Then here I have a rigid member whose length is bi, and at this end again I have a rigid member whose length is bj. Now let's take a look at the degrees of freedom at the ends of the flexible member. So I have d1 flexible, right, d2 flexible, and d3 flexible. Now I have d4f, d5f, and d6f. So these are the degrees of freedoms at the end of the flexible member, and I know the stiffness matrix that relates all these degrees of freedoms, right? But I want to write these degrees of freedoms in terms of the degrees of freedoms at the end of this member. So I have d1 here, d2 here, d3 here, d4, d5, and d6. So basically what I need is the relationship between these degrees of freedom and these ones, so that I can convert the stiffness matrix defined for these 6 degrees of freedom into a different set of degrees of freedoms, right? We see this. We can do that by using the constraint equation. So all I need is a relationship between the degrees of freedom at the end of the flexible member with the degrees of freedoms at the end of our new member. So let's try to define these relationships. So due to compatibility, I should have the same displacements here and same displacements here. Okay? Now I'm looking at this figure right now. And when I look at that figure, this is what I see. d1f must be equal to d1. Okay, so since this member is rigid, this displacement must be equal to that. So that's my first relationship. Now the second relationship, let's say that this one moved by dt amount, so I should have the same translation here, but I have also a rotation, and that will be a rigid rotation, right? This member cannot bend. So because of that rotation, the translation at this end should be larger. Okay, so I can write the following relationship. Let me draw the figure so you can better understand. So initially it was like this. It moved in the upward direction, but at the same time it rotated by d3 amount, right? This is d3, this is d2, and that displacement would be d2f. Then I can write the following relationship. d2f is equal to d2 plus d3 times bi. Okay, so because of having this translation and having a rigid member, this displacement should be larger than d2, and that's the relationship. That's the relationship between these 2 degrees of freedoms. What about the rotation? Since this member is rigid, whatever I see as a rotation at this end, I should see the same rotation at the other end. So d3f should be equal to d3. All right? Now let's take a look at this figure right now, this one, and write down the relationship between these degrees of freedoms. So I got d4f equal to d4, d5f is equal to d5, this time we have minus here, d6 times bj, and the rotations should be equal to each other. Okay. Now let's say that my displacement of the flexibility part is equal to d1, d2, d6, and the displacements of the ends of the member is defined as d1 f, d2, sorry, these should be f's, I'm sorry, let me raise this f here, and that's d2, and it goes up to d6. So if we write the above relationship in matrix form, and this is what I have. I have UF, displacement of the flexible part, is equal to, I'll write it in the following form, T times the transpose of it, you will see why I write it this way, multiplied by the displacements. And then I'll transpose of the transformation matrix will have the following form. So I got 1, 0, 0, 0, 0, 0 here. So there's no d1f is equal to d1. That's what I wrote here. So d2f is equal to d2 plus d3 times bi. So I have bi here. I got all ones and zeros here. And my fifth equation, I have minus bj and 1 in here. So that will be the transpose of the transformation matrix. And I got all zeros here. Okay. Now let's do the same thing for the forces. Now I'll draw the same figure, but this time I will show the end forces. So here, let's show the forces. I have axial force F1, F2, and F3, F4, F5, and F6. Now let's show the forces at the end of the flexible part. F1, F, okay. Now I'm transferring these forces to the end of that member, so I should have the same force, but it should be in the opposite direction. That's F1F, F2F, and the moment it should be in the opposite direction, F3F, F4F, F5F, and moment F6F. Okay. Now I'm looking at these free body diagrams now, and I'm now writing the equilibrium equations. So the equilibrium equations tells me that. Now I'm working on this free body diagram. Sum of forces in the x direction must be equal to 0. So this tells me that F1 should be equal to F1 times F. Sum of forces in the y direction must be equal to 0. I got F2 is equal to F2 F. Sum of moments must be equal to 0. So you can just take moment with respect to that point and then write down the moment equilibrium equation. So this tells you that F3 must be equal to F3F plus the moment due to that vertical force plus Bi times F2F. Okay, then I will do the same thing for this free body diagram. In that case I have F4 that's equal to F4F, F5 is equal to F5F. Now for the F6 I'm taking moment with respect to that point. Then I obtain F6 is equal to F6F. This time I got minus here, F5F times Bj. So as you see, that's the relationship between the forces. Now I will show everything in matrix form. The relationship between F and F will be the transformation matrix, right? And from the constraint equation discussion, we know that the relationship that relates the displacements and the forces will be the same transformation matrix, but one of them should be the transpose of the other. Okay, so let's see if that's true. So in that case, T would be equal to, I got 1, 0, 0, 0, 1, 2, 3, 4, 5, 6. My second equation again, 1, 0, 0, 0, 0. Third equation, I got Bi here, 1 here, 0, 0, 0. The other remaining equations are minus Bj and 1. And that's the other transformation matrix. Okay, and the rest of this equation is 0. Now when you compare these two matrices, that's the one that transforms the displacement, and that's what then transforms the forces, and as you see, they are the transpose of each other. Okay, so once we obtain that, how do we obtain the stiffness matrix? The stiffness matrix of our new element, of this element, is basically you multiply K of the new element is T transpose times element stiffness matrix for the flexible part times T. So when you do this calculation, you will obtain your new stiffness matrix. Okay, if you have any fixed end moment, any loadings, okay, on this flexible part, and if you want to convert these loadings into the equivalent fixed and unbalanced forces at the nodes, you use the following transformation. You did your calculations, okay? At the end, you calculate your displacements at these nodes, okay? And in order to recover the member end forces, the internal forces of this flexible part of the element, you need the displacements at the end of that flexible part, and you can do it by using this equation. And these are the three equations that help us to calculate everything related to the new member that has the rigid and offsets. And when you calculate the stiffness matrix by using the following transformation, we obtain this new matrix, and this is the element stiffness matrix for a member who has the following end offsets. If you want to add the axial forces, it doesn't make any difference on this transformation, on this matrix. You just add the truss part of the stiffness matrix and have 6 by 6. But this is the one with the two rigid end offsets.